Okay, welcome back, guys. Last lesson for us, Chapter 7. Today we're going to talk about scientific notation, something you guys may have seen before. So let's jump right into it. So to get started, guys, I'm kind of give you a little backdrop, a little story. Okay, this is a legend from a long time ago. Okay, but this is the burger legend. Okay, so we have here the Burger King. Okay, loves his burger. He's the king of burgers. Right, and he loves to play a game of chess. Okay, so the Burger King loves chess. So he challenges people to chess games, and every time he's a gambler man too, so he likes to bet on his game of chess. So he keeps winning, keeps gaining all his money and stuff like that, keeps gaining things, and he becomes obviously king. Okay, so all of a sudden there's this guy that comes along, the Hamburglar. Uh-oh. Big guy from McDonald's, the Hamburglar. He comes along. He's good at chess too. So he challenges the king to a game of chess, and he puts this stipulation on it. So the stipulation is this, that every day the hamburger is going to have to give him a certain amount of burgers. After the first day, it's going to be one burger. Let me change the color here. So after the first day, it'd be one burger. The second day, he's going to have to give the Hamburglar two burglars. And every day after that, the number of burgers he's going to give him has to double. So it'll be 4, then 8, 16, 32. So notice how the number of burgers is doubling. 64, and 128. Okay, now Burger King thinking, hey man, I'm not going to lose a game of chess. I haven't lost yet. He doesn't think that he can be beat. Well, little did he know the Hamburglar beats him in his game of chess, and now he's got to go and collect his burgers. He's got to make burgers every day, and starting with the first day, he has to make one burger. So he gets all excited, hey, one burger, that's not too bad. Okay, but notice here that what happens to the number of burgers he makes has to make a certain day. It's getting bigger and bigger and bigger. Okay, so what this is going to show, guys, is what we've been talking about all this chapter, is basically looking at exponents. Okay, if we really take a peek at what's going on here, all right, we start with really one burger at the start, okay? Then we go to two burgers, and from there we go to 4 to 8. And notice here, think about how we get from one box to the next. 1 to 2, I got to multiply by 2. Then I got to multiply by 2 again. So here I start with 2, multiply by 2, multiply again by 2 to give me, so again, 2 times 2 would give me 4. Multiply by another 2, I get 8. Multiply by another 2, I would get 16. Multiply by another 2, I would get 64. Multiply by another 2, I would get 128. So notice that the number of burgers that he would have to make is doubling every day. Okay, so this is an example of exponents. So one challenge I'm going to give to you right now, I want you to think. Okay, if he follows this pattern, he ends right here the first time, he's got 128, but if he continues this and goes all the way across the chessboard, and he's got to fill up the chessboard till the entire chessboard is filled up, okay, how many burgers would he end up owing to the Hamburglar? So the question is, how many burgers would he owe at the very end? Okay, I want you to think about this. Pause, and I want you to think about it. Okay, give you a little hint. Notice here we have day 1. This would be day 2, day 3, day 4, day 5, day 6, day 7, day 8, and so on. See if you can think about how many burgers he would have to owe him at the very last day. Okay? Pause and think. I want you to really give this a try. Did you pause it? You better have paused it. Don't rely on Big Dog. Okay, pause it. See? I knew you wouldn't pause it. Okay? So I'm going to help you out anyway. So here's what I'm going to think about, okay? I know if you really pay attention to this board, it's an 8 by 8 board. So if you think 8 by 8, there's going to be 64 days. How the heck did I get 64? That's just 8 times 8. Okay, so if there's 64 days, how am I going to figure out how many burgers he owes after 64 days? Well, I could go through this process of doubling every single day and keep doubling until I get to 64 days. Well, that's a long time, but if you think about it, okay, using our rules of exponents that we've kind of talked about up to this point, think about your values that you have here, okay? Remember that 2 to the 0th power, at the very beginning, he's going to make 2. That's going to give you 1 burger. Then the second day, or basically after that, you got 2 to the first, which is 2. 2 squared, it's going to be 4. 2 to the third, it's going to be 8. So notice how this pattern is really talking about 2 to some exponent. And what does that exponent represent? Okay, at the beginning it was 1. After the first day it's 2 burgers. After the second day it's 4 burgers, and so on and so on. So basically what happens here is that if I want to find the number of burgers after 64 days, really all I have to do is take 2 to the 64th power. Okay, and that's going to tell me how many burgers you get in a certain day. Now I want you to really do this. Take your phone, your calculator, whatever it is, take out a calculator, and I want you to punch in 2 to the 64th power. Let's see what we get. Okay, plugging that in, here's what you should get. Okay, you should notice you get a really big number. And I'm going to write this at the top here. Okay, your calculator should give you something like this. Mine says 1.844 e to the 19th. Now, what the heck does this mean, e to the 19th? Well, 1.844, that's like 1.8 burgers. That's just about 2 burgers. That doesn't make sense. It should be a really big number. So what does this really mean? Well, what this means is it really represents 1.844 times 10 to the 19th. It represents a power of 10. Now, what does a power of 10 mean? It basically says take 1.844 and multiply it by 10 to the 19th. 10 to the 19th is a really big number. What you end up getting is a value that looks like this. Okay, it's going to be 1.844 followed by 16 zeros. So there I got 6, 9, 12, 15, 16. Okay, so it's 1.844 times 10 to the 19th is that number right there. All I basically did is I took this and moved my decimal. We'll talk about this, but I moved it just 19 times to the right. Well, looking at this number, okay, after 3 zeros, that's 1,000. Then I go to my millions, then my billions. Holy cow, we're going to go on and on and on. Point being is that this is a really huge number of burgers. Okay, what's the purpose of this? Well, first, it kind of deals with exponents, what we're talking about. Second thing is that it relates to scientific notation. Okay, so what's the use of scientific notation? That's our goal to talk about today. Okay, so that really long, drawn-out example, that's just hopefully to give you kind of just a backdrop on why we use scientific notation. Key thing there, scientific notation is when we use really big numbers or the opposite of that, really small numbers. Okay, for example, really large number, I just chose kind of a random distance. Think about distance from the Earth to the Sun. Okay, the actual distance is about 149,600,000 kilometers. That's a huge number if you really think about it. Okay, so instead of representing that really big number, what we can do in science, what we can do in math, is to take that and represent it in terms of a power of 10, in terms of a smaller number. So I can represent this as 1.496 times 10 to the 8th kilometers. This right here is scientific notation, representing it as a power of 10. That's with really big numbers. We can do the same thing with really small. Now this might be a little more relevant, okay? If we look at the mass of a hydrogen atom, what we have here is a decimal point, 0, all these zeros, and then 622 grams. Okay? Now, why is scientific notation really helpful in this case? The last one wasn't too important, but this one, look at all those zeros. This is an extremely tiny number, but it is relevant to things that we may study in science and math. So instead of writing out all these zeros, scientific notation is a shorthand way to write and express those zeros. So instead I can express this here as 6.022 times 10 to the negative 23rd grams. Okay, so what did I do? I basically replaced the zeros with a power of 10, 10 to the negative 23rd. So notice here I have expressed the 10 with the exponent. Same thing here, the 10 with the exponent. So a couple things you'll notice as well. With really big numbers, notice how my exponent was positive. Okay, so big numbers I have a positive exponent, and with this really small number I have a negative exponent. So a couple things we're going to look at there. So first we're going to look at how do we actually write scientific notation, how do we undo something that's written in scientific notation, and how does it actually relate to what we're talking about this chapter with exponents. Okay, first I'm going to show you the long way. So first what we're going to do is take 1 and 2. We're going to look at how do we write these in just standard notation. Standard notation is just write it as a regular number. Okay, so the first example we have is 3 times 10 to the third. So using our ideas of exponent, let's expand this. This means 3 times 10 to the third means 10 times 10 times 10. So powers of 10, that's kind of what we're talking about with exponents. 10 times 10 times 10. Okay, we can simplify that. Well, 10 times 10 is 100. Multiplied by another 10, I'm going to get 1,000. So really this represents 3 times 1,000, which is really equal to 3,000. Okay? So 3 times 10 to the third, scientific notation, is really the number 3,000. Relatively large number. Okay? So we went through this whole painstaking process of expanding these things in really our first section. So there's a shortcut way to do this. All right? 3 times 10 to the third. Notice how I go from 3 to 3,000. The actual number is 3,000. So a short way to do it, when I see 10 to the third, I'm going to imagine there's a decimal. My decimal is right behind the 3. So when I say 10 to the third, notice how I go from 3 to 3,000. So one method you can think about is I'm going to take and I'm going to move my decimal spot 3 spots to the right if I want to go from 3 to 3,000. So my decimal now goes, I'll put it in red, to there. Now where I move the decimal, what I'm going to place is zeros. Okay? And that gives me what number? 3,000, which is exactly what we said it would be equal to. So this is kind of a shortcut way to do it. So all you got to do is basically move the power a certain amount of spaces to the right, in this case, to give you that number of 3,000. Okay, so let's talk about the next one. 7 times 10 to the negative second. Now this one we're going to kind of draw a little bit. 10 to the negative second, we have a negative exponent here. So let's expand this a little bit. Negative exponent, let's move that. This would be 7 times 1 over 10 to the second power. Okay? Now what does 1 over 10 to the second power mean? Well, that is 7 times 1 over 10 times 1 over 10. Okay, 10 squared, I get the 10 to the second power. Now I know we're not the best with fractions, but all you got to do is multiply across. 7 times 1 times 1, that's 7. Okay? 1 times 10 times 10, that's going to be 100. So you get 7 over 100. Now if you punch that into your calculator, 7 divided by 100 is 0.07. So I get 0.07. Now let's kind of relate this back to what we said, the opposite case. Notice here I'm getting a smaller number. So 7 times 10 to the negative second, the negative exponent shows we're going to get a smaller number, actually a decimal, instead of a larger number like we saw in number 1. So let's think of our shortcut way. Okay, number 1, I move the decimal 4 spots to the right to get 3,000. So 3 times 10 to the third, I'm sorry, not 4 spots, 3 spots. So because of this power of 3, I moved it 3 to the right. So notice here I have negative 2. So think of a number line. Okay, if I want to go negative 2, I'm going to move my decimal not 2 to the right, but I'm going to move it 2 to the left. So my decimal is now going to move, and I'll put it in red right there. And what goes in the blank? Well, what goes in the blank is a 0. Okay, so notice if I move the decimal or expand it out, you're going to get the same answer. Okay, but expanding out using the decimal, or sorry, by moving the decimal is actually a lot quicker once you get the hang of it than actually expanding out and showing all that work. Okay, let's take a look and see if we can actually do the opposite. So what we're going to do next is let's take two numbers and write them in scientific notation. So I have 0.00351. Again, this is a small number. What we want to do is write it in scientific notation. So take a look at the last examples we did. I gave you kind of a shortcut way to do it about moving the decimal place. When you had it in scientific notation, moving the decimal place and then filling in zeros and getting your numbers. So let's kind of backtrack. If I wanted to take a look at this number here, if I wanted to backtrack and actually write it in scientific notation, all I would do is have to undo where I moved the decimal. So I moved it 2 spaces to the left to write it as a number to get this, 0.07. If I reversed the process and moved it 2 to the right, that would take me back to scientific notation. So with this, what we're going to do is we're going to move the decimal. In this case, we're going to move the decimal to the right. 1, 2, 3. And I'm going to move the decimal such that I have, and this is the key thing about scientific notation, I'm going to move it such that I only have one number in front of the decimal. Okay? So I'm going to move it to where I have the 3. So I want the decimal now to be 3.51. So I only want one number in front of the decimal. Everything else we can leave behind. Everything else that's non-zero. Okay? Now, this is going to be times 10 to some power. So remember, every time we move a decimal, that's going to represent a power of 10. So how many times did I move it? 1, 2, 3. So I moved it 3 times. So that's a power of 10. But here's the last thing you got to remember. This is a small number. This is a decimal. So when we have decimals or small numbers, we're going to represent this as a negative exponent. So that's going to be times 10 to the negative third. So this would be the answer in scientific notation. Okay? Key thing, I'll just give you a little hint here. To write it in, this is only for scientific notation. Okay? When you move it to the right, that's a negative exponent. If I were to move it to the left, that's going to end up being a positive. Okay? Now, let's take a look at this one. Now we have a bigger number. We have, what is that, 6,710,000. So what we want to do is move the decimal to write this in scientific notation. So again, where's the decimal? It's going to be at the end. I'm going to move it such that I only have one number in front. Now, a lot of people stop right here at the 1. But if I write that, notice I'm going to have 67.1. Is that one number in front of the decimal? And no, that's going to give me 67.1. That's two numbers in front of the decimal. So I actually want to move this one more spot, so it's 6.71. Then it's going to be times 10, and to figure out the power, I'm going to count the number of spaces I move. So that's 1, 2, 3, 4, 5, 6. So I moved it 10 to the, or 6 times, sorry, that's going to be 10 to the 6th. Okay? So here we're moving decimals, and really that power of 10 is going to be represented in how we move the decimal. Hey, now look at this one. That's kind of weird. A zipper as a tongue? I don't know about that one. But what's weird about this is these freaking numbers. Okay? Scientific notation. These are weird. These don't look right to me. All right? This should be weird. It shouldn't be the zipper tongue that's weird. It should be these two numbers. Now, what's weird about them? Let's take about what we just talked about. See if you guys can think about what is wrong with these two numbers. Okay, hopefully you said in your little head of yours that, hey, big dog, there are 2 numbers in front of the decimal instead of 1. So what if we have something already written in scientific notation, but there's 2 numbers instead of 1? Now, with scientific notation, we want only one value in front, one number in front of the decimal. Okay, so here we have 2, so that means we've got to move things around. So there's a long way to do it is basically to do this, okay? Let's undo this. What does 45.68 times 10 to the 5th mean? Well, this means I would take my decimal. To undo it, I would move it 5 spaces to the right, and I would fill in the zeros where they're missing. So 4, 5, 6, 8, and then I'm going to have a 0, 0, 0. So at the end, I'll have 3 zeros. And now to properly write it in scientific notation, let's move the decimal back to the left, such that there's only one number in front. So I can write this now as 4.56. And now let's count the number of decimal spaces we moved. If we count, we got 1, 2, 3, 4, 5, 6. So this would be times 10 to the 6th power. Okay, now how does that compare to the original one? Here I had 10 to the 5th. Here I had 10 to the 6th. So can you look at this and figure out what would be a simplified way to do this? Well, again, what we're doing is we moved. Really, all I did is take this decimal and I moved it one spot to the left. I added an extra decimal spot. Okay, when I added an extra decimal spot, I'm adding a power of 10. So really what you can think about is you're going to take this power of 10, you're going to add 1 to it. 5 plus 1, that's going to give you times 10 to the 6th. Okay, so let's see if we can apply that shortcut here. Okay, I have 24.7 times 10 to the negative 6. So again, I could take this and expand it out. I could undo it and then rewrite it correctly. The shortcut way to do it is I'm going to move this one spot to the left. I want 2.47 times 10. Now to what power? So again, when you add a power of 10, you are literally, think of your rules of exponents, going to add an additional power of 10. So I'm going to add 1 to that negative 6. So what's negative 6 plus 1? Hey, that's negative 5. Okay? So key thing here is scientific notation. You want your numbers to be written with only one number in front of the decimal point. And here's kind of a shortcut way, a quick way to write it correctly and change the power correctly. All right, last step here is let's apply this to what we've been talking about this chapter. We've talked about really 3 rules: the product rule, power rule, and quotient rule of the exponents. Now that we've talked about scientific notation and dealing with powers of 10, when we do some work with scientific notation, we're going to have to apply really the rules we've talked about to this point. So here's an example. What if I multiply two numbers that are written in scientific notation? So 4.9 times 10 to the negative third and 2.8 times 10 to the second. Okay? Well, really you can think of this as a big string of numbers. You have 4.9 times 10 to the negative third times 2.8 times 10 squared, or 10 to the second power. Okay, so notice here we got to think bases. Remember we talked about one rule I told you, treat numbers like numbers. I have 4.9 times 2.8. So with this, I can take those two numbers and simply multiply them out. So I'm going to take 4.9 and multiply that by 2.8, and I'm going to get 13.72. Okay? Then I'm going to treat my powers of 10. Here I have 10 to the negative third times 10 to the second power. So here, 10 to the negative third times 10 to the second power. Notice what am I doing here? Well, I'm applying the product rule. I have the same base of 10, different powers. So what's our rule? Is we're going to take 10 and we're going to take our two exponents and add them together. So negative 3 plus 2. What's negative 3 plus 2? That's negative 1. So this gives me times 10 to the negative 1. Okay, so I've written it in scientific notation. I evaluated my answer, but what's wrong with this? Okay, you should know right away just from the last thing we went through that there should be one number in front of the decimal. So how do I change this? Okay, I'm going to take this decimal, move it one spot to the left. Means I'm going to add a power of 10, so I'm going to add 1 to that negative 1, and I get 1.372 times 10 to the 0th power. Oh my God, what the heck is going to go on? What's 10 to the 0th power? Holy cats and pajamas, we got to add another rule here that we talked about last section. 0 exponents. What's 10 to the 0th power? That is 1. So that really drops out and you get 1. So what's 1.372 times 1? That's 1.372. And that's my final answer. Okay? All right, I want you to pause and do number 8. See if you can evaluate number 8. Ready, set, go. Okay, let's take a look at what you got. So multiplying those together, here's what I did. I kind of skipped some steps, but I treated numbers like numbers. I didn't draw it out like I did here. 3.76 times 8 gives you 30.08. Then I took my powers of 10. I know that I'm ended up going to multiply 10 to the second times 10 to the second. Well, using my product rule, that means I'm going to have to add the exponents together to give me 10 to the 4th. So notice I jumped ahead a little bit there, but hopefully you figured that out from the last example. Then I notice here, decimal, I have two numbers in front of the decimal spot. I got to move it 1 over. So as I moved it 1 to that direction, I'm going to add a power of 10. So I'm going to add 1 to that to give me my final answer of 3.008 times 10 to the 5th. Okay, let's look at number 15 then. Here we have a power rule. So let's say I take 3.7 times 10 to the negative 6. And I'm going to take that and take it to the second power. So let's think of the power rule. Now I can draw this out a little bit. I can write this as, again, this represents 3.7 times 10 to the negative 6 times 3.7 times 10 to the negative 6. I can expand this out and think of this as a product rule. But really remember what happens here with this power of 2. Think of it as, I always like to think as distributive property. I'm going to distribute that power. So that's going to become 3.7 squared. And then you're going to have 10 to the negative 6th squared. Okay, now we can evaluate. So let's go ahead and take 3.7, square that, and put it into our calculator. That's going to give us 13.69. Then here we're going to have times 10. Well, 10 to the negative 6 to the second power. That's using our power rule. So what's our rule for powers? Is we are going to take and multiply the two together. So negative 6 times 2 would give me negative 12. So I get my answer of 1.369 times 10 to the negative 12th again. So last step here again, I've given you this multiple times. Decimal, I have two numbers in front. I need to move my decimal 1 spot over. As I do that, I'm going to add a power of 10. So I'm going to add 1 to that negative 12. That's going to give me 1.369 times 10 to the negative 12 plus 1. Oh my God, oh my God, oh my grr, is negative 11. And there's my answer. Okay? All right, so I want you to apply the product rule, or power rule to number 16. Why it says number 16 there, nobody knows. But I want you to apply the same rule you did in number 16. Ready, set, go. All right, here we go. Let's see what you got. This one I threw a little extra sass in there for those of you that got through the example. So again, what I did, I think power rule distributes. So I distribute this power of 3 to the 7.8 and to the 10 to the 5th power. I got this, 7.8 to the 3rd power is 474.552. Okay, if you rounded it, that's fine. 10 to the 5th to the 3rd power. Again, product rule there. I keep saying product rule, my fault. Power rule, 10 to the 5th to the 3rd power. We multiply the powers together, gives you to the 15th power. Now here's the tricky part, the little twist I threw in there, a little spritz of lemon. Okay, decimal spot, how many numbers do I have in front? I have 3, I only want 1. So I have to move this 2 more spots to the left. That means I don't have to add 1 power of 10 like the last 3 examples, but I got to add 2 powers of 10. So what did I do? I added 2 to the 15 to get 10 to the 17th, and that would be my final answer then. Okay, now last one here, folks. Hopefully you're grinding through. Let's kind of move this up a little bit. All right, let's look at the quotient rule. So again, I'm taking 12 times 10 to the 3rd divided by 4 times 10 to the 5th. So how do I do this? Well, let's think back to what we talked about with the quotient rule. Let's treat numbers like numbers. So let's take and evaluate what the heck is 12 divided by 4. Okay, that's 3. Okay, then let's take powers of 10. 10 to the 3rd divided by 10 to the 5th. So what was our quotient rule for? Remember here we have the same base. We have a base of 10 different powers. What do? We're going to take and subtract my 2 powers. Okay, so what's 10 to the 3 minus 5? What's 3 minus 5? Please don't say 2. Please don't say 8. But it's times 10 to the negative 2nd. And notice, do I have 1 number in front of the decimal? Hey, you betcha, I just got 1 number right here. So that is my final answer. Okay, last one. Let's give it a pause. I want you guys to do number 12. Why is number 12 after number 16? Who knows? We must be in bizarre world. Give it a shot. Pause. Go. All right, let's check it out. Okay, so what I did again, treat numbers like numbers. 2.25 divided by 2 gives me 1.125. I'm going to smile at that one for a hot minute because when I look at that, I see 1 number in front of the decimal. That's going to make it easier. Okay, then I use my quotient rule, 10 to the 2nd divided by 10 to the negative 6. Again, quotient rule, subtract your exponents. Starting with the one on top, 2 minus negative 6. Careful. How many of you said 4? How many of you said negative 4? How many of you said negative 8? My friends, remember, minus and negative, those end up being addition, so that's going to give you 8. So it's times 10 to the 8th. Okay, so what we did here is just applied our rules of exponents to scientific notation. Hopefully you enjoyed. We'll see you in class. Peace.